Hello friends, hello students. Today we will learn about microbial mining and metal biotechnology. So let's begin. Soil microorganisms are very closely involved as catalytic agents in many geological processes. These include these include mineral formation, mineral degradation, sedimentation, and geochemical cycling. In recent years, a new discipline of mineral science, namely biohydrometallurgy or microbial mining, is rapidly growing. Broadly speaking, biohydrometallurgy deals with the application of biotechnology in mining industry. In fact, microorganisms can be successfully used for the extraction of metals. Example: copper, zinc, cobalt, lead, uranium from low-grade ores. Mining with microbes is both economical and environmental friendly. The term metal is used to any substance that is hard, possess, possessing silver luster, and is a good conductor of heat and electricity. Some of the metals, however, are relatively soft, malleable, and ductile. Example: sulfur. Sulfur are this an ore is a naturally occurring solid metal aggregate from which one or more minerals can be recovered by processing. Majority of microorganisms can interact with metals. The metals can be recovered by the microorganisms and by two processes. First is bioleaching and second is biosorption. Now first let's know about bioleaching, or we can say microbial leaching. This broadly involves the extraction or solubilizing minerals from the ores by the microorganisms. Now let's know about biosorption. It deals with the microbial cell surface adsorption of metals from the mine waste or dilute mixtures. Now let's know about bioleaching. In microbial leaching or bioleaching, metals can be extracted from large quantities of low-grade ores. Although recovery of metals, example copper, for centuries, the involvement of microbes in this process was recognized about 40 years ago. The bacteria which are naturally associated with the rocks can lead to bioleaching by one of the ways. First way is direct action of bacteria on the ores to extract metals. Second method is bacteria produce certain substances such as sulfuric acid and ferric iron which extract the metal. That is indirect action. One is direct action, another is indirect action. In practice, both the methods may work together for efficient recovery of metals. Now, let's know about organisms for bioleaching. The most commonly used microorganisms for bioleaching are Thiobacillus ferroxidans and Thiooxidans. Thiobacillus ferroxidans is a rod-shaped motile non-spore forming gram-negative bacterium. It derives energy for growth from the oxidation of iron or sulfur. This bacterium is capable of oxidizing ferrous ion, that is Fe2 plus, to ferric form, that is Fe3 plus, and converting sulfur, that is soluble or insoluble sulfides, thiosulfate elemental sulfur to sulfate, that is SO4 2 minus. Thiobacillus thioxidans is comparable with T. ferroxidans and grows mostly on sulfur compounds. Several studies indicate that the two bacteria T. ferroxidans and T. thioxidans, when put together, work synergetically and improve the extraction of metals from the ores. Besides these two bacteria, there are other microorganisms involved in the process of bleaching, bioleaching. First, let's know about these processes. Sulfolo- uh, Sulfolobus acidocaldarius and S. Breer-Levy are thermophilic and acidophilic bacteria which can grow in acidic hot springs, that is less than 60 degrees centigrade. These bacteria can be used to extract copper and molybdenum respectively from chalcopyrite and molybdenite. A combination of two bacteria, Leptospirillum peroxidans and Thiobacillus organoparus, can effectively degrade pyrite and chalcopyrite. A combination of two bacteria, Leptospirillum peroxidans and Thiobacillus organoparus, can effectively degrade pyrite and chalcopyrite. The individual organisms alone are of no use or in extracting metals. Pseudomonas aeruginosa can be employed in mining low-grade uranium ore, that is 0.02%. This organism has been shown to accumulate about 100 mg uranium per liter solution in less than 10 seconds. Another organism, Rhizopus aerasius, is also effective for extracting uranium from wastewater. Certain fungi have also found use in bioleaching. Thus, Aspergillus niger can extract copper and nickel, while Aspergillus oryza is used for extracting gold. As we studied, among the various microorganisms, T. peroxidans and T. thioxidans are most widely used in bioleaching. The utilization of many of the other organisms is still at the experimental stage. Mechanism of bioleaching is rather complex and not well understood. The chemical transformation of metals by microorganisms may occur by direct or indirect bioleaching. Now, let's know about direct bioleaching. In this process, there is a direct enzymatic attack on the minerals, which are susceptible to oxidation by the microorganisms. For instance, certain bacteria, example T. peroxidans, can transfer electron coupled with ATP production from iron or sulfur to oxygen. That is, these organisms can obtain energy from the oxidation of F2 plus to Fe3 plus, or from the oxidation of sulfur and reduced sulfur compounds to sulfur. And let's know about the reactions. 4FeSO4 plus 2S2SO4 plus O2 gives rise to 2Fe2 whole SO4 whole 3 plus 2H2O. Another reaction is another reaction is 2S. Another reaction is 2S. 2S plus O2 3O2 plus 2H2O gives rise to 2H2SO4. Another reaction is 2FeS2 plus 7O2 plus 2H2O gives rise to 2FeSO4 plus 2H2SO4. As is evidenced from the third reaction given, now we studied, iron is extracted in the soluble form, the iron ore pyrite, that is FeS2. Now let's know about the indirect bleaching. This that was the direct bioleaching. Now we'll discuss about indirect bioleaching. In this indirect method, the bacteria produce strong oxidizing agents such as ferric iron and sulfuric acid on oxidation of soluble iron or soluble sulfur respectively. Ferric iron is or sulfuric acid being powerful oxidizing agent react with metals and extract them. For indirect biology, acidic environment is absolutely essential in order to keep ferric iron and other metals in solution. It is possible to continuously maintain acidic environment by the oxidation of iron, sulfur, metal sulfide or by dissolution of carbonate ions. Now let's know about the commercial process of bioleaching. The naturally occurring metal leaching is very slow. The microbial bioleaching process can be optimized by creating ideal conditions, temperature, pH, nutrient, oxygen and carbon dioxide supply. The desired microorganisms with nutrients acids are pumped into the ore bed. Ore bed. The microorganisms grow and produce more acid. The extracted leach liquor is produced for the metal recovery. The leach liquor can be recycled again and again for further metal extraction. In commercial bioleaching, three methods are commonly used: slope leaching, heap leaching, and in situ leaching. Now, let's know about slope leaching. The ore is finally ground and dumped in large piles down a mountain side. This ore is then subjected to continuous sprinkling of water containing the desired microorganisms. The water collected at the bottom is used for metal extraction. The water can be recycled for regeneration of bacteria. Now let's know about heap leaching. In this case, the ore is arranged in large heaps and subjected to treatment in slope leaching. Now let's know about in situ leaching. The ore in its original natural place is subjected to leaching. Water containing the microorganisms is pumped through drilled passages. In most cases, the permeability of rock is increased by subsurface blasting of rock. As the acidic water seeps through the rock, it collects at the bottom, which is used for metal extraction. This water can be recycled and reused. Now let's know about bioleaching of copper. Copper ores, that is chalcopyrite, covellite and chalcocite, are mostly composed of other metals besides copper. For instance, chalcopyrite mainly contains 26% copper, 26% ore, 33% sulfur and 2.5% zinc. Bioleaching of copper ore is widely used in many countries. This is carried out by the microorganisms Thiobacillus peroxidans, which oxidizes insoluble chalcopyrite CuFeS2 and converts it into soluble copper sulfate CuSO4. Sulfuric acid, a byproduct formed in this reaction, maintains acidic environment, that is low pH, required for growth of the microorganisms. Copper leaching is usually carried out by heap and in situ process. As the copper containing solution, that is copper in the dissolved state, comes out, copper can be precipitated and water is recycled after adjusting the pH around 2. Extraction of copper by bioleaching is very common since the technique is efficient besides being economical. It is estimated that about 5% of the world's copper production is obtained via microbial leaching. In the USA alone, at least 10% of the copper is produced by bioleaching process. Now let's know about bioleaching of uranium. Bioleaching is the method of choice for the large-scale production uranium from its ores. Uranium bioleaching is widely used in India, USA, Canada and several other countries. It is possible to recover uranium from low-grade ores and low-grade nuclear waste. In situ bioleaching technique is commonly used for extracting uranium. In the technique employed, the insoluble tetravalent uranium is oxidized to soluble hexavalent uranium sulfate in the presence of hot H2SO4 by Fe3 plus. Let's know about the reaction. UO2, U means uranium, plus Fe2SO4 whole 3 gives rise to UO2 SO4 plus 2FeSO4. Balancing of uranium is an indirect process since the microbial action is on the iron oxidant and not directly on the uranium. The organism Thiobacillus peroxidans is capable of producing sulfuric acid and ferric sulfate from pyrite FeS2 within the uranium ore. For optimal extraction of uranium by bioleaching, the ideal conditions and temperatures 45 to 50 degrees centigrade, pH 1.5 to 3.5 and carbon dioxide around 0.2% of the incoming air. The soluble form of uranium from the leach liquor can be extracted into organic solvents, example tributyl phosphate, which can be precipitated and then recovered. Heap leaching process is sometimes preferred instead of the in situ technique. This is because the recovery of uranium is much higher with heap leaching. Now, let's know about bioleaching of other metals. Besides copper, uranium bioleaching technique is also used for extraction of other metals such as nickel, gold, silver, cobalt, molybdenum, and antimony. It may be noted that removal of iron is desirable prior to the actual process of leaching. So, let's know about bioleaching in desulfurization of coal. The process of removal of sulfur containing pyrite from high sulfur coal by microorganisms is referred to as biodesulfurization. High sulfur coal, when used in thermal power stations, emits sulfur dioxide, that is SO2, that causes environmental pollution. By using the microorganisms Thiobacillus peroxidans and T thioxidans, the pyrite which contains most of the sulfur, that is 80 to 90%, can be removed. Thus, by employing bioleaching, high sulfur coal can be fruitfully utilized in an environment friendly manner. In addition, this approach is quite economical also. Now let's know about the advantages of bioleaching. When compared to conventional mining techniques, bioleaching offers several advantages. Let's know about these advantages. Bioleaching can recover metals from low grades ores in a cost-effective manner. It can be successfully employed for concentrating metals from waste or dilute mixtures. Third point is bioleaching is environmental friendly since it does not cause any pollution. It can be used to produce refined and expensive metals which otherwise may not be possible. Bioleaching is a simple process with low cost technology. It is ideally suited for the developing countries. The major limitation or disadvantage of bioleaching is the slowness of biological process. This problem can, however, be solved by undertaking an in-depth research to make the process faster besides increasing the efficiency. Now let's know about biosorption. Biosorption primarily deals with the microbial cell surface absorption of metals from the mine waste or dilute mixtures. The microorganisms can be used as biosorbents or bioaccumulators of metals. The process of biosorption performs two important functions. First is removal of toxic metals from the industrial effluents. Second is recovery of valuable but toxic metals. Both these two processes are concerned with a reduction in environmental poisoning or pollution. A wide range of microorganisms, that is bacteria, algae, yeast, molds, are employed in biosorption. In fact, some works have developed biosorbent based granules for wastewater or industrial effluent treatment and metal recovery. In general, the microbial cell membranes are negatively charged due to the presence of carboxyl compounds. Carboxyl, hydroxyl, phosphoryl, and sulfyl hydryl groups. This enables the positivity charged metal ions to absorb on the microbial surface. Now, let's know about the different groups of microorganisms that are used in biosorption process. First is bacteria. Several bacteria and actinomycetes absorb and accumulate metals such as mercury, cadmium, lead, zinc, nickel, cobalt, and uranium. For example, the Rhodospirillum species can accumulate CD means cadmium, Pb, lead, and Hg, hydrogen. Bacillus circulans can absorb metals such as Cu, copper, cadmium, cobalt, zinc. By use of electron microscopy, deposition of metals on the bacterial cell walls was recorded. It appears that the cell wall composition plays a key role in the metal adsorption. Fungi. There is a large-scale production of fungal biomass in many fermentation industries. This biomass can be utilized for metal biosorption from industrial effluents. Immobilized fungal biomass is more effective in biosorption due to increased density, mechanical strength, and resistance to chemical environment. Further, immobilized biomass can be reused after suitable processing. The fungus Rhizopus aeruginosus can absorb several metallic cations, example uranium, thorium, penicillium, lapidarium, P. Spimulosum are used for the biosorption of metals such as Hg, hydrogen, zinc, lead, and copper. Several fungi were tried with some degree of success to selectively absorb uranium. Example: Aspergillus niger, A. oryza, Mucor hamilis, Penicillium cryogenum. Edible mushrooms were also found to absorb certain metals. For instance, fruit bodies of Agaricus bisporus can take up mercury while Pleurotus sajorkazu can also absorb lead and cadmium. Many yeasts commonly used in fermentation industries are capable of absorbing and accumulating metals. For instance, Saccharomyces cerevisiae and Sporobolomyces salmonicolor can respectively absorb mercury and zinc. Now let's know about algae. Several species of algae, that is freshwater or marine, can serve as bioaccumulators of metals. For instance, vulgaris and C. regularis can accumulate certain metals like Pb, Hg, Cu, copper, molybdenum, and uranium. The green algae Hydrodictyon reticulatum absorbs and accumulates high quantities of lead, iron, and Mn, manganese. Some workers are in fact trying to use marine algae, that is example Luminaria olva codium species, as bioaccumulators to reduce the metal pollution in rivers. Now let's know about higher plants in control of metal pollution. Besides the microorganisms till now we discussed are the are some higher aquatic plants, that is aquatic microphytes, that can accumulate potential toxic waste including many metals. Water hyacinths, duckweeds, spirodol species, water lettuce, Pistia statiotes, and certain funds are important in the control of metal pollution. Now let's know about microbial recovery of petroleum. By the conventional technique used in the oil fields, approximately one-third of the oil can be recovered. However, the oil recovery can be enhanced by using solvents and surfactants. Certain polymers produced by microorganisms, that is xanthin, for example xanthin gum, when added to oil wells are capable of increasing oil recovery. Xanthan gum can pass through small pores spaces and promote the release of more trapped oil. In recent years, oil technologists are trying to directly use microorganisms in situ for increasing the oil recovery. In this process, there is no formalized use of a bioreactor. The natural geological site itself is the bioreactor. This allows the water and microorganisms to flow over the ore which are collected after seepage and outflow. The microorganisms through surfactant production, gas formation or by other microbial activities reduce the viscosity of the oil so as to enhance its recovery. However, the success in this direction is not very commendable. Continue, Continued further research may one day help to use microbes for commercial release of oil from oil wells or tar sands. Now finished. Any questions regarding this you can ask me in the comment box. You can subscribe my channel for to know more updates in biotech topics. Thank you.